I'm going to talk today about how to make BitVM quantum resistant. Just kidding. I don't believe in quantum computers. I'm going to talk about something more real. I'm going to talk about the latest iteration of things in the BitVM universe, which is garbled circuits. And first of all, I'm going to start with like a little bit of a recap. What is BitVM about? Well, BitVM is about bridging Bitcoin to second layers, to other systems, because that hopefully improves scalability, privacy, programmability, and makes Bitcoin just way cooler. And what we're doing is we're doing optimistic SNARK verification. Actually, we wanted to have a SNARK verifier, but having a SNARK verifier in Bitcoin is quite complicated, and we cannot update Bitcoin that easily. SNARK verification is complex, so that's not quite possible, but we can do optimistic SNARK verification. And we have like these roles. We have operators that operate the bridge. They process the withdrawals. And if any operator is malicious, then challengers can slash them. And the security assumptions are roughly that we have liveness if at least one operator is live. So you eventually get your money as long as one of the operators is live. And as long as one of the challengers is honest, then nobody can steal money from the bridge. And that improves over the state of the art from like multi-sigs, which are T of n, to a 1 of n assumption. So if just a single party is honest, then the bridge is safe. BitVM 2, the precursor to what we're doing right now, we worked on it for about a year in the BitVM Alliance. The BitVM Alliance is an alliance of roughly 9 companies that are building L2s on Bitcoin. And we completed the implementation this March. And now also the security audit is pretty much fully completed. And very soon, people will launch the first BitVM-based L2s on mainnet. And now we have, ironically, found something way better than BitVM 2, which is garbled circuits. And garbled circuits, interestingly, they have already been introduced in 2021 for DLCs, like discrete log contracts and scriptless scripts. But it took until 25 until Jeremy Rubin published Delbrag and said, hey, this is actually way cooler than BitVM 2. And then he garbled circuit pilled me at the MIT Bitcoin Expo. And then I garbled circuit pilled the BitVM Alliance. And then it turned out that Liam had already been working on something like that. And then he restarted his work. And the research around garbled circuits exploded very quickly. And now everyone is working in parallel on like different garbled circuit implementations. And it's going pretty fast and quite exciting to work on that. And what's funny is that it has already been possible in 2017. Like already SegWit enabled all of this, but it took us 8 years to figure that out. What's the difference between BitVM 2 and the garbled circuits approach? Well, BitVM 2 bridges in general, they consist of 2 parts. First of all, you have that optimistic SNARK verifier, and then you have a bridge contract around that, which is like doing the withdrawal thing. And garbled circuits make the former more efficient. Like you essentially can just verify SNARKs way more efficiently. And the rest of the contract stays mostly the same. So it's basically a drop-in replacement for the BitVM 2 verifier. So roughly the formula is you take the BitVM 2 bridge contract and you take a garbled circuit SNARK verifier, and then you get like a BitVM 3 bridge. And why is that so awesome? Well, the 2 main transactions in the BitVM 2 setting were the so-called assert transaction, where you assert true or proof, and then the disprove transaction, which allowed any challenger to disprove a transaction. And as you can see, they are quite large. Like the assert transaction is 2 megabytes, the disprove transaction is 4 megabytes. So in total, you have to be able to execute up to 6 megabytes of script. You don't necessarily have to execute them. If everyone is honest, then it's very efficient. It's just a few bytes. But you have to be able to execute them, and you have to put up collateral to execute them. And that is, of course, very expensive. It's like 1-2 BTC of collateral. And in that new garbled circuits approach, things become way more efficient because the assert transaction is now only 8 kilobytes, and the disprove transaction is just 200 bytes. So in total, oh, sorry, that's an error. In total, it's like roughly 8 kilobytes. So you get on the order of almost 1000x improvement over BitVM 2. And that's why everyone is so extremely excited about using garbled circuits now. And the rough idea is we have something called conditional disclosure of secrets. That means like we have that black box that we agree on during setup. And once the operator commits to a SNARK, you can feed that SNARK into the black box, and then you evaluate that SNARK in the black box. And if the SNARK was incorrect, then the black box reveals a secret. And knowledge of that secret is a fraud proof. That's the key idea. Like you evaluate the SNARK, and if the SNARK is incorrect, then you learn a secret, and knowledge of that secret is a fraud proof. So you can prove to the chain that the operator lied and provided an incorrect SNARK by providing that secret to the chain. And how does that work? Well, the high-level idea is you garble gates. Like this is a logic gate, like a simple AND gate. I hope you have seen that before. And now how do we garble that? Well, the truth values, like the bits in here, we replace them by labels. Like this is just like random bytes. We choose just random secret values. And now we encrypt them such that the first ciphertext is encrypting the output C0 with the input A0 and B0. So if you know A0 and B0, you can decrypt C0. And if you, here in the second ciphertext, you have if you know A0 and B1, you can also decrypt C0. Or if you know A1 and B0, you can decrypt C0. Or if you learn A1 and B1, then you can decrypt C1. So depending on which inputs you learn a specific output. And this essentially encodes this truth table. So this essentially, this learning A0 means you learned that the value A is 0, and B0 would mean the value B is 0. And then you learn the secret for value C. Does that make sense? Who thinks that makes sense? Huh? I try to explain it again because it's kind of important. So we represent the input values as secrets. Like instead of having 0 here and here 0, we have A0, which is like just 20 bytes of randomness. And this is also just 20 bytes of randomness, and they are all secret. But once somebody reveals some assertion, you can use them as keys to decrypt an output, the corresponding output to the input. And if you learn 0, 0, you learn the output 0. If you learn 0, 1, you learn the output 0. If you learn 1, 0, you learn the output 0. And if you learn 1, 1, you learn the output C1. And this is roughly how garbling a table works. I think I have to hurry up. The important thing is that this is verifiable encryption, so you have to prove during setup that you encrypted it actually correctly. And once you know how to garble a gate, you can compose these gates, and then you can compose them into garbled circuits. I don't want to waste too much time. Well, the challenges is to garble a SNARK verifier, you roughly need to garble 10 billion gates. And that is, of course, a lot. Yeah, and that means you have significant off-chain costs. And the circuit can be quite large, like it can be gigabytes of data. And garbling that circuit also can take a considerable amount of time. And also proving that you garbled it correctly is quite costly in terms of computation. And then there are trade-offs that you can do with the on-chain costs. Like you can make the assert transaction or the disprove transaction bigger and make the off-chain costs cheaper for that. And you can make trade-offs between the security assumptions. For example, you can have more aggressive crypto assumptions, and that makes it cheaper to garble the circuit. Or you could use some kind of trusted computing, like you garble in the cloud, and that is of course way more efficient than garbling on a laptop, but you have to trust the cloud not to reveal your secrets. And yeah, many different schemes are getting explored right now. This is just an overview. You will hear about them in other talks. I think I have to skip over that as well. Yeah, in the BitVM Alliance, we have implemented a gross-16 verifier, actually. And mostly Citrea, Babylon, and Bob have been working on that. Alpen has been working on the Glock scheme that's going to be presented in a few minutes. And yeah, the outlook, BitVM 3 bridges, they still have the same drawback as BitVM 2 bridges, namely they need covenant emulation. That's actually the part that sucks the most about these kind of bridges. So it would be pretty cool if we had input committing covenants. We can do it with CTV in a very hacky way. It's so hacky that some core developers changed CTV to make it impossible to apply our hack. It would be nicer if we had optx hash. That would actually be the clean solution. Template hash is that solution that doesn't work anymore. And yeah, long term it would be great to also get rid of the operators, but that requires something like maybe opmal and great script restoration. Or simplicity. Simplicity would be the perfect solution. Summary, BitVM 2 is almost production ready. It launches soon. BitVM 3s on garbled circuits, they are the absolute future. It's way better than BitVM 2. It's like a roughly 1000x improvement. And the main challenges are taming the off-chain costs of like garbling and like storing the garbled tables. And many different directions are getting explored. Lots of exciting research, and you will hear more about that in the next talks. Thank you.
Hello. Hello, everyone. I'm Ekrem, one of the co-creators of Citrea. Citrea is a ZK rollup on Bitcoin, and today I'm going to talk about how to build bridges with garbled circuits. So let's remember how these garbled circuits work as a black box. We have this challenge transaction, and a watchtower, or we call challenger maybe, can send a challenge anytime, and the operator needs to respond with a proof. If operator fails to respond with the proof, then operator fails. And if the proof is invalid, we can disprove the operator with the garbled circuit scheme. So we have this set up between every pair of operators and watchtowers. And what we want to have is like, if an operator is acting malicious, a watchtower can start a challenge, and then we can kick out the operator. So if we do this, then we don't have to generate garbled circuits over and over and again. The reason why we're doing is because that garbled circuits are expensive, and if we can have this setup, then we don't need to do garbled circuits every time for every deposit. We just do it once at the time of setup, and then we can kick out operators when they're malicious. Of course, multiple watchtowers can challenge a single operator, and that's what needs to happen in the most case. As long as we kick out the malicious operator, it's fine. And the other property we want is if the operator is honest, then that watchtower cannot challenge that specific operator again. So we lose that edge in between. But the trust minimized assumption still holds. If there exists one single honest watchtower, they can challenge if an operator becomes malicious and then kick out the operator. So how do we kick out an operator when they are malicious? The solution is Clementine's round-based mechanism. It allows parallel withdrawals, and single disapproval is enough to stop a malicious operator. So how does it work? We have these round transactions, each having connector outputs. And to go to the next round, the operator needs to wait with a time lock. And we have these rounds up to some pre-signed number. Let's say 1,000 rounds. A kickoff means that the operator is trying to withdraw money from the bridge. What actually happens is that whenever a withdrawal happens, operator pays it and then requests a reimbursement. What we want to achieve is if that operator is malicious, we can stop that and kick out that operator. So, yeah. The key point here is that reimbursement happens in the next round. The reason we do this is because if we can burn this connector output, then the operator won't be able to send the next round, meaning that the operator won't be able to get reimbursement. And then all the next future rounds won't happen. Those TX IDs, those pre-signed transactions, won't happen again. So the malicious operator cannot steal money from the bridge. And this works with multiple kickoffs, right? Operator can do multiple withdrawals in parallel. But if one of them is malicious, we can slash the operator so operator cannot steal any money. OK, so how do we combine this garbled circuit ZK verifier with these round transactions? It's actually simple. We just remember we had this garbled circuit set up between each pair of operators and watchtowers. We simply connect the round connectors with the disprove transaction. We pre-sign the disprove transactions so that they can burn the round connector. So, for a bridge that has bridge deposit denominator 10 BTC, it should support like a lot of withdrawals. Wrap BTC has like 400 BTC on it. It's not trust minimized. But if you want to build a trust minimized bridge, it should support 40,000 withdrawals per operator because we trust that at least one of the operators is honest. So that means we need to have a lot of outputs. We can hide them under other connector outputs, but we need to have these outputs pre-signed. And these are connected to each other. So then what becomes a problem is the dust limit of Bitcoin, because every UTXO has a standardness limit of being at least 330 sats. And if you add up the number, the initial collateral requirement for the round transaction, round connector, becomes really large. The solution we came up with this is using zero-sat outputs. So this makes this round transaction non-standard, but these round transactions are not time critical. So operator can wait until it gets mined and then use the outputs. The good thing is we can spend zero-sat outputs in a standard way. And also the protocol mandates that these zero-sat outputs are burned before going to the next round. Because what we also want to achieve is when the operator is propagating to a next round, operator cannot start any reimbursement requests. So, TOOP is another improvement on bridges with BitVMs. It's found by Feickert Labs. So one of the bottlenecks of BitVM bridges is that operator pays withdrawals and then later gets a reimbursement. This is like a capital requirement. TOP uses this technique where for each deposit, we pre-sign for every subset of operators. And then when a user wants to withdraw, every operator gives their specific private key that corresponds to that withdrawal. And now the user would select which subset of operators they want to get money to, and the withdrawal goes to that address. The key idea is if at least one of the operators is honest, they won't sign anything else, and then the user will be able to get their money back. So as you see here, the reimbursement goes to a subset of operators that the user chooses. And if we have at least one honest operator here, then the user will be able to get the money back. So this way, we don't need to have any like front covering or operators paying withdrawals at all. So the TLDR, with the Garbled circuits, we don't need any collateral to stake. There's no big transactions, no front covering. And users get their withdrawals after a time lock, with the time between the rounds. And it's still trust minimized. So there are some caveats. TOP is good, but it requires exponential amount of pre-signing. Like if we have 10 operators, we sign this for every subset, so we multiply the required pre-signing by 1,000. So the solution is we can use both TOP and the old bridge technique where the operators pays withdrawals. So if the user wants to use the old version, they can still use it. Okay, the other problem is how to prove something about Bitcoin, because in these bridges, the operator needs to prove that it paid the withdrawals. Or we also need to prove that a withdrawal exists in the side system. We need to prove something about the side system as well. Well, if you're a Bitcoin rollup, you can prove the side system state if you know the Bitcoin's state. But still, how do we know the Bitcoin state inside this Garbled circuit is a problem. And we call this Bitcoin light client on Bitcoin. So the solution is we need to get to the longest chain, right? Bitcoin consensus, longest chain. As a normal person, how would you do it? You would ask your friends, like, what's your chain tip? What's your total work? And you would choose the maximum, and then trust that. So we try to simulate this here, where challengers prove the longest chain of Bitcoin. So they prove that there exists a Bitcoin chain where the total work, wait, what's happening? Okay. They prove that there exists a chain where the total work is this big. And this enforces the operator to respond with a longer chain, right? So this is the Schnorr trick we use, where the challenge transaction has an op return of really small but succinct ZK proof of longest chain. And the operator needs to prove there exists a Schnorr signature that is signed by the challenger. And inside that challenge transaction, there exists an op return. And inside that op return, there exists a light client proof. So either that light client proof is incorrect, or the operator knows a longer chain, and the operator acted honestly in this chain. So the idea is, if at least one of the challengers is honest, they would challenge with a correct longest chain. Like they would just prove the Bitcoin main chain, and then the operator now has to talk about the real chain. So this is the actual transaction graph. I don't want to get into details, but I want to talk about something else where with Taproot NX, we can simplify this, and the required number of challenge responses drops by 2x. Why? Because Taproot NX gets signed by the Schnorr signature, but it's not changing the TX ID. So pre-signings are still working, but you don't need to do multiple transactions. But it's non-standard now. Yeah, thank you for listening, and you can read more on our research here.
All right. Thanks to the other speakers for 2 excellent talks. Absolutely. So thanks to the other speakers for 2 excellent talks. Now we're going to talk a little bit more about some of the details and trade-offs that were hinted at in those talks. So I am Aaron. This is Jose. We are from Alpen Labs. We titled the talk at the organizer's suggestion, Engineering the Impossible. But I should tell you that we've already lied to you slightly in that it turns out this is not impossible, just very challenging and interesting from an engineering and cryptographic perspective. And we'll tell you why. So I do research, and Jose does engineering at Alpen Labs. This stuff is undergoing peer review, but it has not been formally peer reviewed. So don't go out and put loads of money on this just yet.
We are not lawyers as well.
No, I wish. So the question we want to answer today is how do we make garbled circuits actually possible on Bitcoin? So garbled circuits are kind of effectively a cryptographic primitive that was originally devised in like
That's
the
kind of
late
the demo.
80s.
After
And
you
they've
do this,
undergone some really excellent
Federation setup,
academic work
you
since
can
then.
connect
But
the
up until
Lightning
now,
Gateway.
as was noted
We
earlier,
don't have time
we
for
really
that
haven't been able to use
right
them
now,
for
but that'd be
anything
the next. That
significant
would be the next
in,
step. So
say,
you
the
can get
Bitcoin
Lightning
space.
payments.
And part of the reason for that is we need some innovations to actually make those happen and make them feasible and engineerable. And let's talk about a few of those now.
All right, cool. Well, thank you.
So we've been talking about kind of like BitVM, BitVM2, BitVM3, which can be used for interesting kind of different kinds of interesting bridge designs. But let's kind of like go a little bit lower and look at kind of cryptographic primitives. So we at Alpen kind of like the term Glock to refer to the cryptographic primitive of a garbled circuit lock. You might be familiar with things like hash locks, which condition the execution of a Bitcoin transaction on revelation of a hash preimage, for example, as the unlock mechanism. In our case, what we want is we want to condition the execution of a Bitcoin transaction on the result of fairly arbitrary computation that is handled by this cryptographic primitive, a garbled circuit. So we call it Glock, a garbled lock. It's a clever little name. The idea is that we have some off-chain and some on-chain work, and we want to minimize the on-chain complexity and move as much of it as possible off-chain. So on-chain, we have whatever our locking script is going to be. We'll talk a little bit more about that later. And we need to be able to unlock it conditioned on the result of this computation. So to do that, we need to establish some authenticated input to the computation. It's important that it be authenticated, so we can't just claim that somebody else did input that they didn't do. We then need some method to move that input off-chain into this garbled circuit. Kind of like, think of it as an encrypted circuit, as Robin hinted at, off-chain. Whatever it's going to do, all of its magic, that we'll hint at later. Then, conditionally, based on whether or not the computation succeeded or failed, is going to reveal a secret. This is conditional disclosure of secrets, if you care about such things. And then we can take that secret, move it back on-chain to if the computation succeeded or failed, then we can condition the execution of the transaction on the unlocking of that locking script. And what this really does is this kind of gives us 3 kind of broad areas of complexity that we need to think about if we want to actually engineer this and make it possible. And I've kind of arbitrarily chosen these 3 things. The first is the input side on chain. We need to authenticate input in an efficient and kind of chain minimizing way. Then off chain, we need to actually design, execute, and engineer the actual garbled circuit machinery, like the guts of this like encrypted circuit mechanism that needs to do all of this magic that we have kind of black box hinted at. And finally, we need to actually figure out how to efficiently execute the unlock mechanism of this garbled lock. And it turns out we can pull some really neat tricks for each of these components. So Jose will start by talking about the first, authenticated input.
So the first challenge, how to do authenticated input. We do that because we want to prevent faulty computation. Traditionally, we do this with one-time signatures, Lamport signatures. And Lamport signatures, we do something it's a hash-based signature, and we bit commit. We sign some bits, but it's very inefficient because we need 2 hashes per bit. And since this is going to be on-chain, this is really inefficient. So what we can do instead, this is something that Liam at Alpen invented, is using adapter signatures, the same Schnorr trick that we do with Music2 and so on, we can use in the authentication of inputs. So what we do is, with the same locking script that is tied to a pub key with a checksig, we can disclosely reveal an adapter or more adapters, and depending on which adapter we reveal, it we can use the same locking script, but with different adapters and different unlocking scripts, we can selective reveal a secret, and that will be the input for the garbled circuit that we are going to do the off-chain computation. This is a trivial case of a single bit, so either one of two secrets, but we can stand this for as many as we want. This can go to as many as we desire. Here is another trivial example with 2 bits, so 4 possible secrets. 3 bits, it's 8, so it keeps doubling like a power of 2. So here with the same locking script tied to the same pub key, depending on which adapter we review, that will generate a valid unlocking script that will review one of those 4 secrets that corresponds to one of those 4 inputs, and this is like a 2-byte input. But we can extend that to 8 bytes or 8 bits or even more. And the result is that Lamport is around 18 kiloVbytes transaction size. And if you use like an 8-bit adapter, with the caveat that this is 132 bytes of authenticated data that we are using as input, we get that this almost like a 9x reduction to close to 2 kiloVbytes. So this is a huge improvement as well for the authentication of inputs.
Yeah, so we can pull interesting tricks using cryptography that is already available to us in Bitcoin in order to properly authenticate input on-chain that is going to go into this off-chain garbled circuit mechanism. So let's take a look a little bit at the actual garbled circuit machinery and how we execute that in an efficient manner off-chain. So garbled circuits are a very general concept for very general computations, but in our case, for like bridge-based approaches, what we really need is we need SNARK verifiers. We need succinct proof verifiers. And then the proofs that we end up reasoning about certain bridge operations in various ways, depending on your design. But this is very general. There are many different kinds of succinct proving systems, SNARKs, and we need to actually select a proving system and then garble or encrypt its verifier circuit, which is what we want for this whole mechanism. So one common approach you may have heard of, called Groth16. This is kind of, I guess, like the prototypical ZK SNARK that most folks who have heard of these have probably heard about. It has a lot of benefits. So it is very standard tooling. The ecosystem makes it very, very well supported. And its proofs are quite small and generally fast to verify. The downside to this is to turn its verifier math into a binary circuit and then garble it. Well, that's fairly complex. The number of AND gates in this circuit, you can decompose a circuit, any circuit, to AND and XOR gates. The number of AND gates is quite high. It's a few billion, and there's even more XOR gates. So as Robin had hinted at before, this has implications. For off-chain work, the time and complexity to actually garble this circuit can be significant depending on how you do it, and it can result in a very large, like basically encrypted output on the order of tens of gigabytes, depending on how you do it. Alpen wondered if there was something that we could do that could be even more efficient than this, and it turns out there is. So Liam Egan at Alpen designed, built, and invented a new SNARK. We decided to call it DV Parry. There's another SNARK that it's kind of based on called Parry. It's a designated verifier SNARK if you care about such things. But we got it to work with ZK VMs such as SP1, which is great for playing nicely with existing ecosystem tooling. And it has an extremely small circuit compared to some others. Whereas the Groth16 circuit was a few billion AND gates, turns out we can get a DV Parry circuit down to, well, we got it down to around 10 or so million AND gates. And we believe that we could get even smaller if we wanted to. So this means that we can get faster and smaller operations off-chain using this particular approach. We also believe that it does, in fact, have the smallest known proofs, smaller than Groth16, which has some minor implications on the authenticated input size as well. So how do we get this efficiency gain? Well, we get it in several ways, and we're not going to go into a bunch of detail on this, but one of which is we can remove the need for pairings. Groth16 requires cryptographic operations called pairings, which can add complexity. But we don't need that. We can make this work with basically any elliptic curve group, any curve that you really want to. In our case, we also select a particular NIST binary elliptic curve. If you care about it, it's SecT233K1, which just rolls right off the tongue. And there's ways to make binary elliptic curves play nicely with binary circuits. They're very fun. We have some material on this if you want to learn about it later. It's very interesting. The trade-off in this is that we do, in fact, though, need extra cryptographic components that must be executed off-chain to make DV Parry work in this way, whereas you don't necessarily need those with Groth16. But once we've selected the SNARK-based proving system that we want to operate on in a garbled circuit, we actually need to garble the circuit. Robin kind of gave some background information on this, but the general idea is that you're going to take a truth table for each of the gates in this circuit, and you're going to encrypt it in very particular ways, and that's called garbling. Now, there's different ways to do garbling. Robin very briefly hinted at this in a slide that he was not able to talk about in detail due to time. But the different garbling schemes in part differ in the number of ciphertexts that you need to actually encrypt each gate's truth table. And I have 3 of them listed here. Kind of the naive approach here, it's often called YOW after the person who ended up kind of inventing this back in the 80s. It requires for each and XOR gate, and XOR gate, it requires 4 ciphertexts for each. This is like the maximal number that you could require for a truth table. Turns out there's cool optimizations, one of which is called free XOR. As you might note, based on these numbers, it means that XOR operations now require no ciphertext due to some very clever approaches, but you still need 4 ciphertexts for each AND gate. It turns out that a Glock design, based on the way that we want to use it, it turns out that you can loosen the security assumptions just a little bit. Turns out you don't need certain privacy assumptions, you just need authenticity, which we hinted at before. And because of that, we can use a really cool newer technique called privacy-free half-gate, or PFHG garbling, which basically minimizes the storage by requiring only a single ciphertext for each AND gate and nothing for XOR gates. And this is great because it helps to minimize the storage of these this off-chain data you need for these garbled circuits, and they're part of what makes some of this stuff feasible at all. Very cool techniques. So we talked about kind of the on-chain authenticated input efficiency gains that we can get. We talked about how we can make garbled circuits work off-chain, and kind of the third component that we hinted at was being able to actually unlock this garbled lock in an efficient way. How do we actually do it? So we need an efficient way to open the garbled lock. As was discussed before, kind of the previous state of the art in this way, which was BitVM 2, well, that required what could be very large scripts in order to kind of run chunks of a SNARK verifier, but on-chain. And to do that means that these unlocking scripts effectively require part of a Groth verifier in particular. And as a result, these scripts could be extremely large. Well, we've already seen that a Glock basically moves all of that computation entirely off-chain to this completely local garbled circuit mechanism. So as a result, we don't need the unlocking script to be some kind of complicated SNARK verifier. Instead, the unlocking script can be just a single signature script, one of the most trivial transactions you could possibly devise. And what's the result? The result is something like this. So I have 3 things listed here. On the left-hand side, you can see the maximum transaction size you could possibly have. It basically is just shy of the 4 million weight unit limit. It turns out there's actually a little header up there that you can't get into that I'll talk about in a second if we have time. BitVM 2, its maximal unlocking transaction was just shy of that at 3,954,000 weight units. Very, very close. Well, it turns out with the Glock, and again, there's different ways you can do this depending what your design is. Our design requires just a nice single signature script that is only 444 weight units. That may be 1 pixel down there on the graph. I don't think so. It's effectively a rounding error. Fun fact, it turns out originally, the BitVM 2 transaction actually used to be slightly larger and actually exceeded this little header-based limit. Our friends over at Babylon actually tried to execute this transaction on-chain to make sure it worked, and it was rejected, which is why we discovered that this little limit actually existed. We didn't even know it was there. So we re-engineered it to bring it down slightly below it. But still, it's very large. So what do we get at the end of the day with some of these really interesting engineering innovations and approaches? Well, we get a huge success. So we've seen that using garbled circuits for this kind of disputable computation for bridge applications, it's just a major, major win. But it's a major win that does require very careful and frankly very clever engineering in a lot of different ways. It requires us to be really careful about how we do authenticated input, and we saw that we can pull a trick with adapter signatures to get a very low on-chain footprint with existing cryptography on Bitcoin. We've seen techniques for garbling circuits. We can use different kinds of proving systems like DV-Parry, different kinds of garbling schemes like PFHG to get low off-chain footprint in time and space. And on the unlocking side, we can replace very large scripts that do things like chunked SNARK verifiers with extremely small, trivially small signature unlocked scripts. So what does this give us? Well, it gives us efficient, very modular and flexible, and very frankly, clean to engineer, understand, and audit bridge designs. We're really excited about this, so hope you're excited about it too. So thank you very much.
Okay, hello. Yes, so I'm Srivatsan. I'm a senior researcher at Babylon, and I'm here to talk about trustless vaults. So this is a very interesting twist on the bridges, and yeah, we'll see what it is. So, we have heard 3 talks about building Bitcoin bridges. Ultimately, what's the goal of these, right? You have Bitcoin, huge assets sitting on Bitcoin, and then you have smart contracts on other chains, and you want to be able to use Bitcoin on these smart contracts on chains or rollups or whatever. And so people are building bridges, but the truth is that the bridges look something like this. Maybe Robin showed you that fancy Golden Gate Bridge style bridge, but I'm showing you a different picture. What do I mean here, right? So Robin did talk about this. So even though you have all this BitVM stuff, you still end up requiring some intermediaries in this bridge protocol. So we are better than multi-sig bridges where you had to trust a majority of a committee. We are better in the sense that you need to trust only one out of a certain set of parties, but then you still need these. You need signers for covenant emulation. You need operators for facilitating the bridge. You need some challengers or watchtowers, and you need at least one of. You need to trust at least one of these guys, to be honest. Well, okay, we got a bit better, but if you look at Nakamoto's vision, then his vision was to build a system based on cryptography, crypto proofs instead of trust, right? So we have got a bit there, but not all the way. So, we at Babylon were thinking, we are trying our best to get to this vision of a system that's based entirely on crypto proof instead of trust. So we asked, okay, we tried to build bridges, but bridges is only one way of being able to use your Bitcoin on applications, right? Can we do it natively? Can we use native Bitcoin for DeFi activity on other chains? And so let's dissect this a bit more. What kind of applications do people want to use with their Bitcoin, right? So here's an example, Bitcoin-backed lending. So the thing about Bitcoin is that people want to hodl it naturally. So people want to use Bitcoin as collateral in DeFi protocols, not really to sell it. And one of the best use cases for using Bitcoin as a collateral is lending. So Bob, a borrower, wants to deposit Bitcoin and get a loan of USDC to pay his bills, right? So there are 2 parties here. There is Bob, the borrower, and there is Larry, the lender, who lends USDC on, let's say, Ethereum. And basically what you want to encode is 2 conditions of withdrawing this Bitcoin, right? If Bob repays the loan, then Bob should be able to get back the Bitcoin. But then Bitcoin price fluctuates, right? So there is a possibility of the loan being under-collateralized, in which case there is a liquidation event. So, which means if the Bitcoin price, major typo. If the Bitcoin price is less than 50K, then the lender should be able to take the collateral, Bitcoin. Whereas if the price is above 50K and Bob repays the loan, he can get back the Bitcoin, right? So simple application. And for this one major application, let's see how we can build something that doesn't require a bridge. And so maybe let's try to learn from one of the first successful projects on Bitcoin, which was Lightning, right? So how does Lightning work? There are again 2 parties, Bob and Larry. They set up a channel, and this payment channel allows either Bob or Larry to withdraw from the channel, right? So they could sign a transaction that collaboratively settles the balances. But then importantly, this payment channel also allows each party to withdraw trustlessly from the channel. Like if Larry doesn't participate or just goes malicious or something, Bob can trustlessly withdraw the money he put into the payment channel. That's the kind of property we want, right? And so inspired from this, we designed sort of the Bitcoin vault architecture, where these two parties together co-sign, there are only these two parties, Bob and Larry, who can withdraw from the Bitcoin vault. So this gets rid of the operators, gets rid of any bridge operators, because you can already encode the addresses of these two parties into the Bitcoin scripts. It gets rid of any covenant emulation requirements. So you don't need these signer committees, because Bob and Larry can themselves co-sign the Bitcoin transactions, just like payment channels or Lightning. Bob and Larry co-sign the transactions, so you don't need anyone else to emulate covenants. And also, you don't need any extra challengers or watchtower parties, because Bob and Larry can challenge each other, just like it happens on Lightning. And so what we end up with is a trustless protocol, where you don't need any additional parties except Bob and Larry, who are the borrower and lender here. So essentially what Bitcoin Vaults is doing is it's taking the trustless nature of Lightning and adding onto it the garbled circuits that the previous three talks talked about, in order to enable much wider set of possibilities beyond just payments. So it's kind of taking the best of both Lightning and these garbled circuit-based bridges. Okay, so this was kind of a simple story. Bob, Larry, they do peer-to-peer lending. What we really want to do is being able to integrate Bitcoin with existing lending markets. So, for example, Ethereum has so many different lending protocols already there. Morpho, Aave, Euler, and all these lending protocols. And we want to be able to integrate Bitcoin with that economy, right? So that's what we are doing. So we are building the first integration of native Bitcoin with the Morpho lending platform on Ethereum mainnet. So the way it works is that borrower can lock Bitcoin into a vault, and he can borrow USDC, let's say, from Morpho on Ethereum. And when he repays the loan to Morpho, he can create a proof of repayment. This is a SNARK proof, which then gets verified on Bitcoin through the garbled circuit mechanism that my friends talked about earlier. So that's the borrowing. Who's the lender? So the way these markets work is that there are lenders who supply the loan assets into the contract on Ethereum, and then those assets are used for supplying the loans. And of course, there is a liquidation event that I talked about. And generally, there are another set of parties called liquidators who can, if the loan goes under collateralized, they repay the loan. They pay USDC to be able to claim the Bitcoin collateral. So, similar to repayment, those guys can also generate a proof of liquidation and use that to withdraw from the trustless vault. So even in this architecture, the protocol remains entirely trustless for the Bitcoin holder, because he can lock Bitcoin and then use a proof of repayment of the loan to withdraw from the Bitcoin vault without trusting any of the other actors. So that's what we are building. And right now, in fact, fresh tweet from today, we are performing a mainnet experiment for the end-to-end integration from locking Bitcoin into a vault, taking a loan on Ethereum, repaying it, and getting back your Bitcoin. So we have been working hard for the last 2 months building this, and we will be running an experiment, publishing the results live on X. So if you guys are interested, you can follow Babylon or DN Say, who is our one of the founders, and you can watch the updates live. But I can show you right here a glimpse of some of the results, right? So the last 3 talks talked about garbled circuits and how to make them more feasible and so on. Well, I'm here to show you it's already feasible. You don't need any more complicated cryptography. You don't need any more additional research. It's already feasible. So we already did the mainnet experiment just yesterday, actually, for running this garbled circuit, right? So there are two main transactions here. One that posts the inputs of the garbled circuit on chain, and one that posts the output. So Aaron just in the previous talk spoke about these transactions. So these are already pretty feasible. So the garbled circuit inputs, the size is about 70 kilobytes. Yes, with some more research and more advanced cryptography, you can bring it down to something like 8 kilobytes. But this already costs only about $100 of transaction fees. And yes, the garbled circuit outputs are pretty small. It's just one hash lock verification, so something like 300 bytes, and costs $1 to pay on chain. And we are already kind of overpaid fees, just to be careful. But yeah, it's pretty low fees and feasible right now. And something that the previous talks did not talk about is the off-chain costs. So this garbled circuit stuff involves, kind of pushes the cost, minimizes the cost on chain, and pushes some of the cost off chain. But it's not that bad. So to generate one garbled circuit, you need to store the garbled circuit, which costs about 300 gigabytes of data. The setup time for generating the garbled circuit and verifying that it was garbled correctly currently takes about 3 hours to do that. But there can be more optimizations, and with more new cryptography, we can improve that. And the garbled circuit evaluation time, though, is very small. So it takes only about 4.5 minutes for one of these parties to be able to challenge in case of a malicious attempt to withdraw from the vault. So that's the experiment. And yeah, be on the lookout on X for the results. A lot of people to thank for this, for being able to get to this stage of the trustless vault. And if you're interested more about trustless vaults, here's a link to the white paper. And also, if anyone here is interested to come join us, then we are looking for Bitcoin devs and also ZK devs. Yeah, that's it. Thank you.